talk to you about fast Danksharding. So just a quick motivation. So we're talking about data availability, which is required for L2 scaling solutions such as rollups. And Danksharding is a data availability sampling scheme, which is part of the solution. And it allows for a lot of data, blocks of 32 megabytes, to be used by rollups with fast verification. And to do that, it uses Reed-Solomon erasure codes and KZG commitments, and those are computationally heavy. The reason we deal with Danksharding in Ingonyama, we do acceleration for ZK, and those building blocks are generally used for ZK snarks, and we are generally dealing with accelerating those. So the building blocks such as NTT, MSM, and ECNTT. And in general, what we have is we have the SRS, which is generated in the KZG ceremony. It consists of 4,096 elliptic curve points, and we get the block, in, which we view it as composed of 256 blobs. Each blob is composed of 4,096 scalars. So in total, we have 32 megabytes in this block. And per blob, we need to do three things. One is to construct a blob commitment. This is this branch. We interpolate the blob, so we interpolate in two directions. So the blob of 496 gets twice as long to 8K, and we also interpolate the number of blobs times 2. So you can see also the number of commitments is per interpolated blobs, which is why there are twice as many as the number of blobs. And also, the third branch, we construct proof for each sample of 16 scalars within each blob. So in total, we have a matrix of 512 on 512's proofs. The commitments and proofs are elliptic curve points, and the interpolated data is made of scalars. So this is our architecture. You can see the three branches. So this is the commitment branch, the interpolation branch, and the proof branch. The color coding tells you whether we're dealing with scalar field arithmetics or elliptic curve arithmetic. And the border for each block tells you what's the computational primitive we're using. So if it's a thick border, such as here, we're using MSM. If it's a dotted border, this is NTT or ECNTT, and a regular thin border would be some sort of vector manipulation, which is in general linear. And the way we make this fast, we do a few things. One is we're using linearity to reduce the computational codes, and I'll explain specifically what that means. We're maximizing the use of processing, so whatever we don't have to calculate when constructing the proofs and the interpolations we're doing beforehand in pre-processing. We're making sure to make everything maximally parallelizable. And we make sure that the building blocks themselves are designed for efficiency. We're using a minimal set. As I said, we design them for efficiency. So optimizations using linearity. So the first thing we do is look at the Reed-Solomon encoding. And the naive approach for that would be to first interpolate the data, 0 pad, so it's twice as long, and then evaluate the data. Interpolation meaning inverse entity, and evaluation meaning forward entity. And the evaluation part is an entity which acts on 2n variables. And in total, we our two entities, the number of multiplication is given here. So half n log n for the first entity and half 2n log 2n for the second entity. This is the usual naive approach. And in our approach, we do something a little different. We interpolate, we modulate, and then we evaluate, where the modulation is multiplying each row by corresponding roots of unity. And then when we evaluate, we don't do a 2n entity, we just do n-sized entity, so that we only calculate new data. We don't recalculate our old data like the naive approach was doing. So now we only have 2 times half n log n multiplication plus the n multiplication needed for the modulation. And in total, we're saving a total number of half n log n. This is per blob or per row. Okay, so this is one way we can use linearity to reduce the number of operations needed by just not recalculating existing data. Another way of using linearity and moving things into preprocess is by noting that KZG commitments, they use the SRS multiplied by the inverse entity of the data. And since the inverse entity is just multiplying with a matrix, and this is a symmetric matrix, we can multiply with the matrix on the left, on S, and actually do the inverse entity of S and multiply that by the data. This part, the inverse entity of S, we can now do in preprocessing, and thus we save doing the inverse entity. Now you can say that this doesn't really matter because we're going to need this action of inverse entity of the data in the interpolation branch anyway, and that is true. So what we really are saving here is we're shortening the longest path to reduce latency. So we're reducing this dependency of the commitment branch in the interpolation branch, so now we can do them in parallel. So in total, this method reduces latency, and the exact same idea is also used in the proving branch, and it includes reshaping of the data and overall normalization. So every action that is linear, we can kind of move to the pre-processing and save on multiplications. And this has nothing to do with Danksharding, but I can tell you that this exact same trick was used in our ALIO miner. And there, it doesn't just reduces latency, it really reduces a lot of the computation time, move it into pre-processing, and making a very efficient miner. Okay, another thing, and here I'm gonna ask you a question. Let's view two approaches for the proving branch. This branch, we can do one of two things. We can either repeat this branch once for each interpolated blob. We repeat it 512 times. Or we can do it once for each blob, 256 times, and then interpolate times 2. And the question is, which is going to be faster? So let's do some rough computations. The main bottlenecks are the EC entities, and if we do it 512 times, what we're going to get is 512 times 2, because we have 2 entities, one inverse, one forward, and 1/2 512 log 512, which in total we get 18 times 256 times 512. In addition, we also have 512 multiplied by the time it takes for these two actions, the row multiplication and the fold and sum, which are linear actions. So this is kind of a second order thing, smaller than the time it takes for the EC entity, but this is also part of it. Alternatively, we can repeat the proof generation 256 times and then interpolate the columns like we did before. We do I entity and another entity to get the interpolated data. And this will take, now it's 256 times 2 times 1/2 512 log 512, and then another 512 times 2 times the time it takes to do the entity for half this number. And in total, when you do this computation, you get 17 times 256 times 212, which is shorter than this number by a little over 5%. And the time it takes for the first two operations is half, because now we only need to repeat them 256. Okay, I hope you're able to follow my computation. If you haven't, the idea is that we can do two things: either repeat the computation 512 times with these numbers of multiplications, or repeat it 256 times and interpolate and get these numbers. And it seems obvious which is faster, right? And the answer is this is faster. Okay, the one with the bigger numbers. Why is that? The reason is we can parallelize this better. Okay, so we're gonna implement this on a GPU, and the GPU can do a lot of things in parallel, and this can be fully parallelized. So this 512 times repeating this computation, we can do them all in parallel. While if we take the second approach, we're going to have to do 256 things in parallel, and then do some more actions sequentially after that. Okay, so even though this appears to be taking longer, when you consider parallelizing your computations, this is actually faster. So we're implementing this entire thing using ICICLE, which is our company's library for doing these kind of computations on GPU. It's implemented in Rust and CUDA. It uses fast EC entity based on pipe MSM, batched entity and EC entity for high parallelizability, and it currently only supports BLS 12.381, but there is planned support for more curves. And let me tell you a little bit about the benchmark, how fast this entire thing is. So we tested it on a setup with RDX 390 Ti GPU, and these are our benchmarks. So for the commitment branch, we got 440 milliseconds, while the competition, Rust KZG, takes a little faster. This competition is used on CPU, and actually the difference is due to the communication between the CPU and GPU in our solution. So a few tens of milliseconds are lost there. However, you can see that the interpolation and proof branch is much, much faster. The current benchmark is 4.6 seconds compared to more than 30 seconds. And this is actually still gonna get faster. This uses about a third of the CUDA cores at any given time. So we still have room for more parallelization there. This is going to get even faster. Our development roadmap includes complete on-device flow, so making sure we are not losing any time on communication between CPU and GPU. optimizing multi-precision and multiple modular multipliers, which are the most basic building blocks of our calculations. They're still going to be optimized. Integration with Ethereum, and EC entity improvement in ICICLE. This is currently the longest bottleneck, and there's still some room for improvement there. And of course, support variable size inputs. This is all. Thank you.